Hello, my Science Alliance, my IGCSEs. So, we're on our second to last module of this whole IGCSE course. On my website, we've got nearly everything saved on there that I've ever taught. We're going to do a few more lessons on radioactivity, and then astronomy module after this, and then that's it. So this is the second radioactivity lesson. I don't think you really need to have come to the first one, to be honest. We're going to do a little bit of recapping and a little bit of just making sure that you're really comfortable with the words that we use to talk about atoms and things. Sorry, loft conversion, it's not very exciting. And then, yeah, we'll gently start thinking about radiation, and we'll carry on with that next week. All right, so for those of you who weren't here and those of you who have forgotten, very quick recap of what we did last week, right? Atoms, they are protons and neutrons, otherwise known as nucleons, in a central nucleus. So it's already very confusing. So we've got nucleons, the neutrons, and the protons, which are in the middle of an atom, and that is what we call the nucleus. And then we've got electrons whizzing around the outside of it. So this, we did that last week. We also covered this, but I thought probably wouldn't hurt to just talk about it again. Can you tell me, if you were here last week, what is the nucleon number of lithium? What's the proton number? What's the atomic number? What's the mass number? What is Z? And what is A? If you're hearing about all this for the first time, I reckon you could probably tell me the proton number. You could have a good guess. And you probably have a very good guess at the nucleon number as well. If you're watching this on catch-up, you've got a distinct advantage because you can just pause it, do all the answers at your own pace, and then carry on. But if you're watching live, that's more exciting, isn't it? I'm going to be quiet and let you get some stuff done. Have you done that? We'll go through it fairly quickly, because if you know it, you know it, and if you don't know it, you're probably quite cross that I haven't taught you it. So the nucleon number is the number of nucleons. That's all right, isn't it? So the protons and neutrons, they're both nucleons. So it's just all the number of particles that are in this middle bit, really, the nucleus. So that's number 7. The proton number is the number of protons. So that's 3. That's all fine, isn't it? The atomic number is the same as the proton number. So the atomic number is also 3. And the mass number is the same as the nucleon number. It's just a different word for it, and it's good that we get used to saying both names. So the mass number here is also 7. Remember, because we looked at last week how electrons basically don't weigh anything. If you're ever doing any maths at this level about how much an atom, what its mass is, you can just ignore electrons because they're so small. So the mass of the atom is just the mass of the nucleus, and we say, remember, that the kind of relative mass of a neutron and proton is just 1. Oh, right. The way to remember it is that science hates you and is awful. So A does not stand for atomic number. So Z stands for atomic number. So Z is 3. Z is how many protons there are in a nucleus. I know, I don't know. Just the A is the mass number. So that is 7. Okay, so if you just remember science hates you and wants you to be confused, you'll get it right every time. So nucleon number and mass number are the same. And A is that as well. Proton number and atomic number and Z, that's all the same thing. It sort of depends on which exam you're doing, what you'll end up saying. Okay, here's that, just to recap. I've got some lithium here, and there's a number 3 on it and a number 7 on it. And I've said that the number 3 is the number of protons, otherwise known as the proton number, otherwise known as the mass number, otherwise known as Z. And the number 7 is the number of protons and neutrons added together that a lithium atom has in its nucleus, otherwise known as atomic number, otherwise known as nucleon number, otherwise known as A. But I've made a terrible mistake. 2 of those things need switching. Which 2? So 3 is the number of protons. It is the proton number. It's not the mass number because that includes neutrons. So let's switch atomic number and mass number, and then that's right, okay? The atomic number is the same as the number of protons. Got that? Brilliant. All right, have a little look at this then. Gasp, Lara, what have you done? It's okay. I've just moved the numbers because this is more likely how they'll show it to you at IGCSE. So this time we've got a big capital F, which stands for fluorine, and we've got the number 19 at the top of the F and the number 9 at the bottom of the F. So go on. It would be lovely if they asked you this at GCSE, wouldn't it? What's the nucleon number of fluorine? What's its proton number? What's its atomic number? What's its mass number? What's Z? What's A? And how many neutrons has fluorine got as well? You should be able to work that out. So the nucleon number of fluorine is how many protons and neutrons it's got all together. So that's going to be the bigger number, right? So it's 19. The proton number is how many protons it's got, which is going to be smaller. So that is 9. The atomic number is the same as the proton number, so that is also 9. And the mass number is the same as the nucleon number, so that is 19. And A is not atomic number, so Z is atomic number, so Z is also 9. A is the mass number, so that's 19. And to get the neutrons, well, if you know that there are 19 neutrons and protons altogether, and there's 9 protons, then you just take 9 away from 19. So fluorine has 10 neutrons. That's sort of fairly standard IGCSE radioactivity question. Okay, have you got all that? Do it all again. Go on, just to really make sure that you've got this. Do it with carbon. Carbon's got a big 12 at the top and a 6 at the bottom. Trying not to hum the countdown theme tune, because that's really passive aggressive. It just always comes into my head when I'm wanting to get started again. Do 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 bum. The nucleon number of carbon is 12. It's got 12 protons and neutrons added together. The proton number is 6, because it's the smallest number. That just makes sense. The atomic number is the same as the proton number, so it's also 6. The mass number is just the mass of the carbon atom, and we don't count electrons because they're tiny, so that's also 12. The A doesn't stand for atomic number, so Z is the atomic number, so Z is 6. And A stands for mass number because science hates you, so that is 12. And to get the number of neutrons, you do 6 protons, take away from 12 protons and neutrons added together, so it is 6 neutrons as well. Phew. Okay, let's move on a little bit then. So it's the number of protons we have talked about before that decides what the atom is. So here we've got an atom of lithium. It's got 3 protons with 3 electrons whizzing around the outside and 4 neutrons in the middle. It can have different numbers of electrons and still be lithium. It could lose an electron and it would still be lithium, as I'm showing you here. And it can have different numbers of neutrons. Just get one away with my favourite PowerPoint effect. So that's still lithium because it's still got 3 protons. It's the protons that decide what the atom is. And we looked at last week how atoms with different numbers of neutrons are called isotopes. So here we've got 3 isotopes of hydrogen. One's got 1 proton and no neutrons, one's got a neutron added, and one's got 2 neutrons added. They're all hydrogen atoms because they've all got 1 proton each, all right? They're just isotopes of hydrogen. So having a wonky amount of protons and neutrons can make an atom unstable. So the hydrogen with just 1 proton, that is stable, that's your standard hydrogen. A heavy hydrogen, if you add a neutron, that is also stable. You can get hydrogen that's got 2 neutrons, but it doesn't like it. It's very unstable. And the nucleus basically like emits particles or energy to become stable. And that is what radiation is, basically. So some elements, here I am showing you a periodic table with some of them shaded in yellow. Some elements don't have any stable isotopes. God bless them. Some of these are ones that humans have sort of discovered by smashing things together, but they've only existed for like a few split seconds and then they've disappeared because they're so unstable. A little note here, it's quite easy to think, oh, well, it must be having loads and loads of neutrons that makes a nucleus unstable. It's not exactly just having more neutrons, it's about the imbalance of protons and neutrons. It's to do with ratios. So I've done this little thing to try and get it into our heads, how it's ratios, right? So let's just say that a nucleus has got 6 protons and 18 neutrons. That wouldn't happen. I'm just giving you small numbers as an example, right? Let's say we've got this nucleus, I've lined them all up here, there's 6 protons and there's 18 neutrons. That's the ratio of that. If I split all these neutrons and protons apart and share them out, you can see that each proton can buddy up with 3 neutrons. So that would be the ratio, right? That's the ratio of this particular atom, 1 proton for every 3 neutrons. So if we get rid of 2 protons and 2 neutrons, so we've lost the same amount of protons and neutrons, what happens to the ratio? Maths is beautiful, isn't it? You've lost 2 protons and 2 neutrons, the same amount of protons and neutrons, but now the ratio is completely different. Now the ratio is 1 proton for every 4 neutrons. So that's a very, very oversimplified example of how it's not the amount of things you lose, it's the ratio that makes the nucleus unstable. All right, let's get on to alpha radiation. So to become more stable, there's different ways that a nucleus can emit radiation. This one is called alpha radiation. To become more stable, some nuclei release an alpha particle. We talked about alpha particles last week. They are 2 protons and 2 neutrons joined together. So this is the nucleus, one nucleus, and more than one nucleus, you say nuclei. I'm really sorry, that's just Latin for you. But yeah. Alpha particles, we looked at them last week. We said they were quite big and very fast moving. Well, that is what one is, 2 protons and 2 neutrons. If an alpha particle has 2 protons and 2 neutrons, what element is it, technically? Just this little thing, just this little alpha particle here, flying quickly through the air. What atom could you say that is? What element is it? It's made of 2 protons and 2 neutrons. I'm saying atom, I should say nucleus really, shouldn't I? It's not got any electrons whizzing around it, but it's a nucleus of a certain atom. It's helium. You could call it a helium nucleus. It's just another word for an alpha particle because it's got 2 protons, so it must be helium. Okay, so when an atom decays, it's totally random. Completely random. There's nothing you can do to make a nucleus decay. I'm just going to say hi to you because I haven't seen you for a while. You can't get an unstable nucleus and just like give it a shake or hit it with a hammer. There's nothing you can do. It's just totally random. Nobody knows when that nucleus is going to emit radiation. All right? Good. Glad we sorted that out. Here is a radioactive material. This is plutonium-238. That means it's plutonium and it's got 238 protons and neutrons mixed together. If you're thinking, that doesn't look very stable, you are correct. It contains trillions of unstable nuclei, but there's no way of saying when one of them will emit an alpha particle. All right then, how much have you understood? Let's just start you off with hopefully a fairly simple question, which a lot of people are getting wrong. Americium-241 has 95 protons and 146 neutrons. Okay, so I've just pulled out a little bit of the periodic table for here for you. We've got americium, and we've just got one number on it, 95. That's its proton number. Yeah, its atomic number. So it's got 95 protons and 146 neutrons. It's not a very stable element, isn't americium? It gives off an alpha particle. What element is it now? Is it the same element or is it a different element? If americium gives off an alpha particle, what element is it? This was this was confusing people on Facebook yesterday in quite a pleasing way. I don't want you to get everything right straight away. If americium, which has an atomic number of 95, gives off an alpha particle, then what element is it? It's lost 2 protons, isn't it? It's lost 2 protons, and this 95, this is its proton number. So it's now neptunium. Good, isn't it, eh? Like magic. So americium emits an alpha particle, and it is no longer americium. It's changed into neptunium. Here's the way that the exam might put it, if you ever do this for IGCSE physics. We've got uranium-238 here. That's the most common isotope of uranium. Okay, it's got a proton number of 92 and it's got a mass number of 238. So it decays, that's what this sort of arrow means, into a particle of thorium, a nucleus of the element thorium, and an alpha particle, which we can also call a helium nucleus, right? So here's helium with a mass number of 4, because it's got 4 protons and neutrons altogether, and an atomic number of 2, because it's got 2 protons. Is that okay? Depending on how you're feeling about this, could you tell me how many protons and neutrons does uranium-238 have? And can you see how to fill in these gaps? Can you see how to work out how many protons and neutrons, or, well, just fill in the gaps. Give me the mass number and the atomic number of thorium, if you can. It's just brain exercise, because I haven't told you what to do. Well, I've told you what to do, I haven't told you how to do it. Just be quiet, Lara, and let everyone work, okay? How are you doing? How many protons and neutrons does uranium-238 have? I didn't tell you to bring a calculator, but some of you might find that a bit weird. Well, it's got 92 protons, because that's its proton number. It's the number of neutrons. I would be very happy if you'd written it had 238 minus 92 neutrons, but if you can do that in your head, then the answer was 146 neutrons. So how are we going to fill in the gaps on this thorium particle? Well, the amount of protons and neutrons that a thorium nucleus has and the amount of protons and neutrons that a helium nucleus have got to add up to equal the number of protons and neutrons that uranium has, right? I will show you for why with a little picture, because no protons and neutrons have disappeared. It's like the original uranium nucleus before it decayed has to be the same as the thorium nucleus plus the helium nucleus, right? Because they don't just disappear, do they? So you should have got, or the answer is, that thorium has 90 protons, yeah? Because uranium's got 92, it loses 2, so it turns into thorium, which has got 90. And again, you've just got to make sure that this mass number plus helium's mass number equals uranium's mass number. So the answer was 234. Okay, I've told you that one. Can you do this one? So this is the famous radium that Marie Curie did a lot of work with. Radium's got an atomic number of 88 and a nucleon number of 226, and it decays because we know it's alpha decay, in fact, don't we? I wouldn't even have to tell you, because here we have an alpha particle here, a helium nucleus. It decays into radon and helium. So what's the mass number of radon and what's the proton number of radon? How you doing? So the answer is, you've got a nucleus with 88 protons in it, and it gives off 2, so whatever we're left with has got 86 protons, right? And it started out with 226 protons and neutrons altogether, and it's given off 4 protons and neutrons, so it must have 222 protons and neutrons altogether, and that is the answer. It does. So it's 222 and 86. Okay, let's move on, because I've got a little puzzle for you, which some of you who'd already read about physics, how dare you, without me, knew the answer to. But if you don't know the different types of radiation, I'm very excited that I get to tell you this. There are other types of radiation. Carbon-14, as an example, has 6 protons, obviously, because here it is on our simple little periodic table. It's got an atomic number of 6. And how many neutrons has it got? Carbon-14 has got 6 protons. How many neutrons has it got? It's got, come on, It's called carbon-14. It's got 6 protons. So it's got 8 neutrons. And it decays in this special amazing type of radiation. And a nucleus of carbon decays into a nucleus of nitrogen. What? How does a carbon atom just turn into a nitrogen atom? What's happened here? It can't be alpha decay, can it? It can't be. That's not what happens in alpha decay. And it's not really a clue, but a new weird piece of information. It hasn't lost any protons or neutrons. I mean, has it? It hasn't. The number of protons and neutrons in it don't change. It's weird, isn't it? Here's a picture. So you've got carbon-14, it's got 6 protons and 8 neutrons. How does that turn into this thing that's got 7 protons and 7 neutrons? Well, the answer is one of the neutrons of carbon-14, seen flashing here, turns into a proton. Oh, I know! A neutron just turns into a proton. So you've still got the same amount of protons and neutrons all together, but you've lost a neutron and you gained a proton. Amazing! So some of you might be thinking that doesn't seem right, and it's not really right. We heard in our energy lessons ages ago that energy can't be created or destroyed. Charge is sort of behaves in a similar way. Charge has got to be conserved. In physics, it's just a basic law of physics that negativity and positivity can't just pop out of nowhere. It has to what we call be conserved. So what actually happens is a neutron turns into a proton, so we've got like an extra positive charge. How does that fit with the laws of physics? Well, something else is created inside the nucleus. What must be created to keep charge the same as before? We've got an extra positive charge that has just appeared. What has to appear with it? Pew! An electron! And that is what happens. An electron just gets made inside the nucleus. An unstable nucleus decays, a neutron changes into a proton, and an electron gets made as well. Awesome. And this is called beta decay, or beta minus decay, technically, because you can think of it as the minus means that an electron is given off, okay? So here I've got a little kind of mathsy bit for you of beta decay happening. Mull this over for me, please. So we've got, can you do this? Fill in the gaps here. We've got a carbon particle that's got 14 protons and neutrons altogether, and 6 protons, and it's decaying into nitrogen, which has got 14 protons and neutrons altogether, and an electron. So can you fill in the gaps? Like, what's the proton number of nitrogen? What's the proton number of an electron? What's the mass number of an electron? How are you doing? A bit weird, this one, isn't it? Should I go through it? So you started out with 6 protons, but it's beta minus decay. So a neutron has turned into a proton. So now its proton number, I should have put that on the board for you really to give you a clue, sorry. A neutron decays into, say, a proton, and an electron is released. So you've won an extra proton, so the proton number has changed to 7, and the electron doesn't have a mass number, does it, or an atomic number? That wouldn't make any sense. It's not got any protons or neutrons. It is an electron, so sorry, that was a little bit mean. They might do things like show you this in your exam and say, what kind of decay is this? And you would have to spot that an electron had been given off, and therefore it was beta minus decay. Phew, all right then. We will leave it there, and next week we will look at the last kind of radiation that you need to look at, and also how all these different types of radiation behave as well. Yeah, and then like I say, there are a few more lessons of radioactivity, no more than 5 after this, I don't think. I think we'll easily fit it in before the half-term holiday. and then astronomy after that. But I'm going to give you, I think I've got 4 questions for you, just to check that your brain has taken that in. Here is boron. It's got a number 11 and a number 5 next to it. Can you tell me how many neutrons does boron have, please? How many neutrons in a typical atom of boron? Hopefully you've got it already, but if you haven't, here's some multiple choice. Has boron got A, 5 neutrons, B, 6 neutrons, or C, 11 neutrons? The answer is, well, it's got 5 protons, and it's got 11 protons and neutrons mixed together. So if you do 5 take away 11, you're left with 6 neutrons. So the answer was 6. Next question. What is A? Oh, what is A? What do you reckon? Can you give me both names for A? Can you tell me in your own words what A is? Yeah. I'll put your multiple choice up. Is A atomic number, B proton number, or C nucleon number? Which one of those is represented by A? The answer is, well, remember science hates you. I should stop saying that. It's not atomic number, and it's not proton number, because that's the same as atomic number. It is nucleon number. It's the number of protons and neutrons added together. That is A. Atomic number is Z. 3, what type of decay is happening here? We've got a neutron, which is sort of turning into a proton, and an electron. What sort of decay is that? Here's your multiple choice options. Is it A, beta minus decay, B, alpha plus decay, C, beta plus decay, or D, alpha minus decay? That was hard to say. The answer is, it's beta minus decay. Yeah, hopefully fairly easy to remember because the electron is given off and the electron's got a negative charge. And finally, can you fill in these gaps for me? Ooh, can you fill in these gaps? We've got a plutonium nucleus here with a, well, the number at the top is 239 and the number at the bottom is 94, and it's decaying into a uranium nucleus and a helium nucleus. So can you tell me what the big number at the top and the number at the bottom would be on the uranium? The answer is, well, it's given off 2 protons, so it must have 2 fewer protons, and it does, 92. And it's given off 4 neutrons and protons mixed together, so we need to take 4 away from 239, and you get 235. Splendid. And that is the end. Sorry, my loft conversion is making quite a lot of noise, but it's worse for them because it's absolutely pouring down. Right, you lot. So join me next week when we will be learning about gamma radiation, and also we haven't looked at all about how these different types of radiation behave and why people get so freaked out when you talk about radiation. So we will look at that next week. I'm just going to go over to my Facebook page because whenever I'm live on YouTube, I've always put a post up on my Facebook page saying, you can comment on this, you can't comment on YouTube, but you can comment on this, you can say hello if you want to. So I'm just going to see if anyone has said hello. I am certain you will have many glowing reviews. Oh, good. Archie Wave is here. I nearly said hello to you because I was thinking that you would be watching, so I'm very glad that you are. because I would have been disappointed in my head if I wouldn't have showed it out loud. No pressure. But I'm glad you're here. Hello, good to see you. Thank you for coming, you lot. And hello to all the lurkers as well. Also very grateful for your presence. Thank you for joining me. If you want to support me, you can go to my About section on YouTube. It takes you to a website called Coffee, and you can sign up to get my magazine. It's a very good magazine. It should be. It takes me absolutely blooming ages, doesn't it? But it will be if you are supporting me. I'll tell you when to get excited. It's not back at my house yet, printed, so I can't put it into boxes and stuff, but it's at least out of my head, which is making me feel a lot better. So thank you so much for all your support. You are obviously the only reason that I can do these lessons for free. I really appreciate it. It'd be awful if I had to start charging. Yeah, so thank you. I'll see you next week for another radiation lesson, or tomorrow at 9 a.m. if you want to come to my all ages lesson on nutrition, or tomorrow at 10:30 if you want to learn about African versus Asian elephants in Lego Story Show. But until then, thank you very much for watching.